Hello, my name is Akshay Chaturvedi, and I, along with my teammates, have made a project on image caption generator. So, first of all, what is image caption generation? The caption generation is a real-time application of natural language processing in which we get generated text from an image. The generated text is capable of not only describing the contents of the image but also giving a suitable caption to the image. This project is inspired from Andrej Karpathy's famous blog post, which is the unreasonable effectiveness of recurrent neural networks. For this project, I have used the dataset, which is Flickr 8K dataset. Let me give you a brief description about the dataset. The Flickr 8K dataset contains around 8091 images and around 5 captions for each image. So totally there are 40455 captions in the dataset and 8091 images. I have provided the Kaggle link for the dataset also. So for the evaluation matrix, I'll be using Blue score, which is bilingual evaluation understudy score. It is a metric for evaluating a generated sentence to a reference sentence. A perfect match results in a score of 1, whereas an imperfect match results in a score of 0. The score was developed for evaluating the predictions made by automatic machine translation systems. So this was a little bit brief about my project. So I'll be now describing my code. So first of all, we'll have to import the necessary libraries. All the necessary libraries I have imported here, and also I have configured the GPU for my notebook here, and I'll be setting a seed of 123. uh, by setting a seed of any number specified, it reduces the randomness and makes uniformity in the data distribution. So next up, I will be downloading and importing the dataset in my notebook. For the images dataset, in my directory, I'll show you. Yeah, so this is my Flickr 8K dataset directory. This is the image dataset that I'll be using. There are 8091 images here, and from my text, this is the token dataset. Yeah, it contains all the captions for images. Both these dataset I'll be using for my analysis. So first of all, I'll be importing the caption data. So here I am reading the file, text file, and now I'm storing the data in a list called data text, and then after I am creating a df.txt data frame, which will contain uh, all the captions for images like this. So here, as you can see that for each image, this is the same image repeated five times. Yeah. So this is the same image from 0 to 4 repeated 5 times. There is a caption associated with it in our dataset. As you can see, 0, 1, 2, 3, 4. These all are the captions for the same image. And here also, here's a different image with the 5 captions, so on. I've taken example of only 6 rows. So now I'm just going to show some example pictures with captions. So as you can see, there are 5 pictures here, and along with each of these pictures there are 5 captions associated with it. So first of all, for this picture there are these 5 captions. For these pictures there are these 5 captions, and for these 3 pictures also there are 5 captions each. So now I'll be doing the data preparation or preliminary data analysis. So for this, first of all, I'll just create a new data frame, which is called as df word, to visualize the distribution of words. It contains each word and its frequency in entire tokens in decreasing order. Okay, so I'm just showing the 3 top rows for this. So here, as you can see that for the word A, it has came 62989 times, around 63,000 times in my data set. The period has come around 36,000 times in my data set, and the word in has come around 19,000 times in my data set. So I'll be making a histogram to calculate the top and the least frequently appearing words. So for the top 50 most frequently appearing words, it is a period in the. So these are the 50 words that appears the most in my data set, and these are the words that appears the least in my data set. So I'll be just cleaning these words which appears the most and which appears the least, so that it does not affect the model performance. Sometimes these words can make the model bias, so we have to remove these. So in order to clean the caption, we'll create three functions, which are remove punctuation, remove single character, and remove numeric character. So for example, I have taken an example string, which is this string, and now I'll be creating these three functions: remove punctuation, remove single character, and remove numeric. And after implementing these three functions on this string, we'll see the output. Okay, so this was my example string. So after removing punctuations, we have got this this string. uh, as you can see that these punctuations are now removed, and now after removing the single character words like I and a, we get this kind of a string, and after removing the numeric values, we get this. So it looks more clear, and it's more effective for our data set to make good predictions. So I'll be now applying all these functions. For now I have just applied these functions on just one string. So now I'll be applying these three functions on my entire caption data set. Yeah. So after applying this to my entire data set, I'll again count the 50 most occurring and 50 least occurring words. Here these are. So after cleaning my captions, we can see that our vocabulary size is significantly reduced by 200 words. We can say that 200 useless or 200 biased words we have removed from our data set. Yes. Now for our captions, we'll be adding start and end sequence token for each and every captions, so that our model can see when the caption starts and when the caption ends. Now image preparation for the VGG16 model. So we are using the VGG16 model in our dataset. VGG16 model is basically an image model which takes the input of image shape 224, 224 and 3 metric. And why we have chosen this VGG16 model instead of other models like MobileNet and others, because the VGG16 model achieves an whopping accuracy of 92.7%, which is around the top 5 test accuracies in the world. uh, and it has trained on 14 million images belonging to 1000 classes. So I have downloaded the weights on my local machine. So this is the link for the to download the weights for the VGG16 model. So now now I'll see the architecture of this VGG16 model. So as you can see, this is the architecture of my model, and in the end there is a dense layer which is a softmax layer basically, and which predicts the 1000 classes of the images. So first of all, it creates 4096 features for each image, and then it predicts that among the 1000 classes, which class do that image belongs to. Basically, this is what a VG16 model does. So for my image caption generation project, I don't need this classification. I just need the features for these, the 4096 features for each image. I don't want the 1000 layer prediction for my 1000 class prediction for my image. So I'll just remove this last layer from my architecture, and I'm left with this. Yes. So now I'll be applying the VGG16 model to all my dataset images, which is 8091 images. So this cell alone takes around 2 hours to execute, because it applies uh, the VGG16 model architecture to all my 8000 images. So as you can see, for each image there are 4096 features. I'll show you. Yeah, this is how the features look like. Now I have linked the text and the image data. Now extracting one caption for each 8091 images in dCaption. So for the dCaptions, I have extracted one caption for each 8091 images instead of 5 captions, which was at the beginning. I am taking only one caption. And D images, in the D images, I have taken all the 4096 features for each image respectively. So as you can see, the shape of D images is 8091 cross 4096. So basically for each image we have 4096 features, and top 5 rows for the D caption uh, is like it's like this: start sequence, end sequence, and it's our caption. Start sequence, end sequence, and in between we have a caption. Yeah, so the next thing is tokenizer. So now we'll be for our model to predict, it does not understand this language, so we have to tokenize it so that we can feed it into our model along with the image. So for tokenizing, we have used the Keras, the library from the Keras preprocessing text, which is tokenizer. So I have tokenized my all the captions which are in dCaptions, and I have stored them in a in a data frame called dText. So as you can see, this caption here after tokenizing looks like this, array here. This captions after tokenizing looks like this. One is for start sequence and two is for end sequence, and in between we have this captions. So now I'll be splitting the dataset in training and testing. So for splitting the dataset, we are splitting it in the ratio of 6:2:2, where 6 is the training data, 2 is the validation data, and 2 is testing data. So for all our images, uh, captions, and images names, we have split it all of these in 6:2:2. After this, we'll be padding the captions for each image, because why we need the padding is because to feed the captions to our to feed the captions to our model, we need the uniformity in the length of the captions. So if a caption is very small or if a caption is very large in length, and if we feed it to the model, it will create a non-uniformity which we do not want. We want a uh, uniform model which predicts good captions. So basically what we are going to do is we are going to do the padding. So in the padding, if the length of a caption is very small, it will pad it to the maximum length. It will pad it with zeros to the maximum length for the each for likewise, if the length is very small, it will pad it to it will make it big so that if we can feed it uniformly. Yeah, so as you can see, now I have in my X text train, this is one caption look like. So this array of 14 elements, this 2 cross 2 array of 14 elements is uh, yeah. So as you can see that, I'm sorry. So as you can see that this array consists of only one caption. So for one, it's the start sequence, and 75, 38, 33, these are the tokenized caption words. So why we have done it, like why we have splitted the caption like this, is because we are going to feed each array to the same image. For example, if an image belongs to a caption, we are first going to feed it with the start sequence and let it predict what's the next word. After it has predicted the next word, we are going to show it the true word, which is 75, and it after that it is going to know that how much it differs from the original word, and after 75 it will predict the next word, and after it has predicted the next word, will show the true word, which is 38, and so on. So by token by token, we are predicting the captions here. So this is our model. This is our base LSTM model architecture. So the LSTM model architecture takes the input of image, which is of the shape 4096, and for the LSTM model we have used 256 units. Mhm. And the loss is categorical cross entropy loss, and the optimizer is Adam. This is the whole architecture of our LSTM model. So after configuring the model, we'll fit the model. So after fitting the model, it took around 11 minutes to fit the model, and as you can see, after every epoch the loss is reducing significantly. First it was 5.29 and it has reduced to 3.29 after 5 epochs, and but the validation loss has reduced till 4th epoch 4.39, after which it has increased. This is the graph. As you can see, the loss is reducing, but the validation loss has reduced till 3, and then it has started increasing. So this is our main function, prediction image, which takes the input of the prediction uh, and which takes the input of an image and then predicts the text for us, which is our generated caption. Now yeah, as you can see that these are the examples. For this image our model has predicted this, like so on. So now coming on to the blue score, which is our evaluation matrix. For the blue score, if the image has a blue score for more than 0 0.6, I'll be categorizing it in good caption, which is prediction good list, and if the image has a blue score less than 0 0.3, I'll be categorizing it in the bad caption, which is prediction bad list, like this. So as you can see, this is some of the examples from my good prediction list, and these are some of the examples from my bad prediction list. So I'll now be plotting the images from with good caption and bad caption. So as you can see that the true caption is child in pink dress is climbing up the stairs in an entryway. So this is the image, but my model has predicted boy in red jacket is sitting in front of the backyard. So it's a worst caption. Black dogs and spotted dog are fighting, as you can see in the image, but my model has predicted that black and white dog is running in the air, which is bad. And likewise, for this image, brown dog is running in the sand. My model has predicted brown dog is running in the snow, which is quite good considering the considering that it has been predicted by a model. So for this, the blue score is 0.80. Likewise, the good captions are here. So now I'm going to show you a demonstration of graphical user interface. So for this graphical user interface, there will be two functions, which is upload image and caption, to get the generated caption for the image. So I'll just going to run the graphical user interface. Yeah, so this is my GUI looks like. So I'm going to choose one of the images from my dataset. I'm going to see how efficiently it predicts the caption. So this is my data set. Any random image I am going to choose. Yeah, so as you can see, it has predicted the caption, which is man in white shirt is standing in the water. So some things it has predicted quite nicely. Those are that there is a water here, and a white shirt is also seen. It we as we can say that there are two human beings, but our model has seen only one man, and it assumed that it is wearing a white shirt because a white entity is here, and there's a water and the man is standing. So some things it has predicted quite well.